Okay, we're going to start. We've started. I turned on the recorder. Let's see. We have a homework that's due. It was due tonight, but I shifted it back to tomorrow night. But this one is pretty short. I don't think it's difficult, although there may be things in there that are confusing. I was going to look at two problems just to remind you of something but we've said it multiple times in class. This homework is more challenging though, because this involves solving equations using inverse trig functions. And remember, you get lots of solutions to those equations. And so writing down the solutions is messy. And so that one's going to be harder. This one's not due till Monday, however. If you have questions about it now, I'm happy to answer those. But also, if you work on it before class Monday, so that if you have questions about it on Monday, you can ask them in class before it's due that evening, right? Okay, so work on it over the weekend so you'll know what your questions are. But if you have questions now about this one, anything on this homework, I will discuss those. It's going to probably be questions about typing in answers or, well, maybe finding the answers too. Also. Okay. So let's see. Remember, ideal for attending Zoom means you must have passed the second test, but I think everyone today, at least who is on Zoom there, did that. So that's good. Let me open this. Let me open this homework, and I just wanted to look at just a couple of the problems here at the end. Some of these are going to be using your calculator, so we'll need your calculator. Some of them, though, you really don't need your calculator. So, for instance, in number 7, it says find the exact value of this expression, right? So that's sine inverse of 2. Okay, so normally, right? Okay, inverse functions like sine and sine inverse here will simply cancel each other. And so in many instances, when you're composing inverse functions, you would just get as the answer here 2, because the sine and the sine inverse would cancel each other. But you have to keep in mind, right, that that this sine inverse and this, which is the original sine function, are not quite completely inverses of one another. So so in most cases, these things will cancel each other, but there are some slight discrepancies, right, that you have to be careful of. In this one, if you think about what is the sine inverse of 2, of course, you may want to try to evaluate that with your calculator. So you might try, typing in 2 with your calculator and then using the sine inverse key on your calculator to compute that. I think it's going to come out as an error, right? Yeah, undefined. Because remember, when you're writing that expression sine inverse of 2, what you're really finding here is an angle, right? Remember, sine inverse yields an angle. And so you're looking for an angle here whose sine is 2, but there is no angle whose sine is 2, right? Because how big does the sine function get for any angle? Yeah, the biggest is 1 and the smallest is -1, right? Okay, so there is no angle whose sine is 2. So you could have also seen this without your calculator, right? Oh, there's no such thing as sine inverse of 2. Okay, and so therefore this value is undefined, right? So you cannot compute the sine of it. So the answer here is undefined. So this is kind of a trick question. Now, on the other hand, in 8, this one's a little bit easier. We want to compute the cosine inverse of the cosine of pi over 6. Okay, so if you just try doing this on paper, again, normally, right, these functions will cancel each other, correct? Because they're inverses of one another. So in most instances, when you compose a function with its inverse, they should just cancel. So the answer here should be pi over 6, right? Ideally. But let's see what really happens. So let's try evaluating it carefully inside out, right? So computing a cosine of pi over 6 first, and then finding its inverse, right? Okay. So let me lower the screen here and let's write that one down on. Let's write that down so in the notes somewhere. If I can find a blank sheet in the. If I can find a blank sheet in the notes. Let's try it right here, where in the notes we're going to start with, right here in the margin. So what we're asked for there again is the cosine inverse of the cosine of pi over 6, right? So we're hoping that's going to turn out to be pi over 6, but let's see what happens. So what is the cosine of pi over 6? Let's just go ahead and compute that. You don't need the calculator, right, to compute the cosine of pi over 6. What is the cosine of pi over 6? Pi over 6 is a special angle, right? So what does that turn out to be? Pi over 6 is 30 degrees. So what's the cosine of 30 degrees?
Square root of 3 over 2.
Yeah, that's square root of 3 over 2, right? Okay. So that's square root of 3 over 2. And so now we're trying to compute the cosine inverse of the square root of 3 over 2, right? So we're looking for an angle now whose cosine is square root of 3 over 2, right? So, well, the logical answer there is pi over 6, right? The first angle cosine is square root of 3 over 2, right? Is pi over 6. The thing you have to be careful of, though, is to make sure that the angle that you write down here is in the proper range, correct? Or cosine inverse. So that's why I kept stressing, right? You've got to remember ranges for these inverse trig functions. What is the range for cosine inverse? So when you apply cosine inverse, you always get an angle between what two numbers? 0 and pi, right? Okay. So we want to write down pi over 6, Evan, and we just have to make sure, is that between 0 and pi? Is it? Sure, right. Okay. So fine. This is all that's all good, right? So the answer indeed here is pi over 6. So these inverses just cancel each other, right? And we just end up with pi over 6, just like we had hoped for. But in the next problem, they're going to change this just slightly. So they're going to write, I think it's 11 pi over 6. Let's look back at that next problem. If I can find the right screen here. Not that one. I thought I had it there. Did I close it? What did I do with that? This thing is getting in my way is the part of the problem there. That's the calculator. Oh, well, we can just reopen it there. So in the next problem, right, we want the cosine inverse of the cosine of 11 pi over 6, right? So a very similar problem, right? Okay. And so when we start doing this, right, we might think, oh, well, you know, I've got to get just the same answer out of this, right? Okay. So let's go through the calculations. So cosine of 11 pi over 6, let's draw a picture of that just to remind ourselves of what this looks like. Where is 11 pi over 6? You draw that. Yeah, it's in the fourth quadrant. That's almost 2 pi, right? 11 pi over 6 is almost 12 pi over 6. 12 pi over 6 is 2 pi. So we're in the fourth quadrant, right? Almost one full revolution, right? But not quite, right? So here's 11 pi over 6. Whoops. Here's 11 pi over 6. And so what's our reference angle then? There between the terminal side and the x-axis. what's this angle? 30 degrees, right? So that's pi over 6. So the cosine of 11 pi over 6 is going to be the same as the cosine of pi over 6, right? Except we may have to adjust the sign. But we're in the fourth quadrant. What's the sign of the cosine in the fourth quadrant? What, Iris? Positive, right? Because remember, the cosine is associated with the x-axis. X-axis is positive in the fourth quadrant, right? So, so the cosine of 11 pi over 6 is just the same as the cosine of pi over 6, and that's square root of 3 over 2. So we're back now to just computing the cosine inverse of square root of 3 over 2, right? And so you might want to write 11 pi over 6. You might think these things cancel each other, but we just discovered, right, that no, that's not the case. The cosine inverse of square root of 3 over 2 is what? It's pi over 6, not 11 pi over 6. Why can it not be 11 pi over 6? Because what's the range of the inverse cosine? We just said it, 0 to pi. 11 pi over 6 is not between 0 and pi, right? Okay. At any rate, so the cosine inverse of square root of 3 over 2 is pi over 6. So see, these things don't match, right? So in this case, these two quote unquote inverse functions do not really cancel each other. All right. And that's just because of the fact that the inverse cosine function is not quite the inverse of the original cosine function. Remember, it's the inverse of the restricted cosine function, not the original cosine function. But it's still useful, okay? Still useful to us for lots of reasons, but it's not, doesn't quite obey the laws of inverse functions. Fortunately, we're talking today about exponential functions and logarithmic functions, which are also inverses of one another, and we don't have this issue, okay? The natural log function is the true inverse of the natural exponential function. Okay, let's see, what's the last problem if I didn't mess that up again? So here's the inverse tangent of the tangent of minus pi over 4. Okay, let's see if we can do that one too while we're thinking about it. I just put that one right here, right? So let me erase this and we'll right over this. So maybe this will be easy, right? Like we're hoping these inverse composition problems are easy, but maybe it'll be a little bit more difficult. So the inverse tangent of the tangent of minus pi over 4. First, we have to remember what the tangent of minus pi over 4 is, right? So if you draw a picture of that, minus pi over 4, that's going to put you in the fourth quadrant, right? You're going to go in the clockwise direction, right, into the fourth quadrant. So there's minus pi over 4, which means that its reference angle is pi over 4, correct? So the tangent of minus pi over 4 is going to be similar to the tangent of pi over 4. That's kind of obvious, right? You just have to worry about getting the right sign. In the fourth quadrant, what is the sign of tangent, though? The thing to remember is tangent is sine over cosine, right? Tangent is sine divided by cosine. So think of it that way. The sine is what sign in the fourth quadrant? Sine, S-I-N. It's negative. Cosine, though, is what? Positive. So for tangent, you have negative divided by plus, right? And so that's negative. So so the tangent of minus pi over 4 is going to be minus the tangent of pi over 4. What is the tangent of pi over 4, though? I think that was on the test. What is the tangent of pi over 4? What? What? Y'all are speaking so softly. What? 1. Yes, it's 1. Okay. So the tangent of pi over 4 is 1, but we have to change the sign to minus because we're in the fourth quadrant. Now we have the inverse tangent of minus 1. Okay. So we need an angle right, whose tangent is -1. Well, that looks like it's got to be minus pi over 4, correct, right? Because that is an angle whose tangent is -1. But we have to make sure, so we're thinking, oh yeah, okay, so my candidate here is minus pi over 4, just like I would expect, right? It looks like these two things are canceling each other, and I get an answer of minus pi over 4. But again, you've got to make sure you're in the proper range. What is the proper range for tangent? Tangent. Remember, tangent is sine over cosine. So the range for tangent is the same, range for tangent inverse, I mean, is the same as the range for sine inverse. What's the range for sine inverse? For cosine, it was 0 to pi. What is it for sine inverse? What? Go ahead, Evan. What? Negative pi over 2 to what? That's it. Minus pi over 2 to pi over 2. So you have to get an angle that's between minus pi over 2 and pi over 2. Is that between minus pi over 2 and pi over 2? Minus pi over 4? Yes, right. Okay. That's between minus pi over 2 and positive pi over 2. Ah, so that's got to be it, right? That's got to be the right answer here. So see, these things did cancel each other, right? They cancel each other just like we would hope for inverse functions, and we get an answer there of minus pi over. Okay. So that's always kind of the tricky part of applying, of using inverse trig functions, is this issue about the range of inverse trig functions. Okay. All right. So, well, so there's a few problems from the homework that's due now tomorrow night, right? Okay. And then, so finish that, and then make sure you bring questions with you if you have them about next homework where you're solving equations. That's also going to involve a lot of using a lot of inverse trig functions, right? Okay. So this homework is just kind of a warm up to that homework that's due on Monday. That's going to be more challenging. All right, let me switch back to the notes here, and here are the notes. So last time we were talking about, or what we learned about last time, was the natural exponential function, right? Okay, the natural exponential function. Actually, there's two natural exponential functions. There's e to the x, that's one of them. Okay. And then also e to the minus x is the other one. But mainly we're focusing on just e to the positive x power, okay? And that's, but anyway, both of those functions are called natural exponential functions. They're called exponential because the way the formula is formed, right? You have a base, and then your input variable x, right, is part of the exponent of that base. And you have a very special base there, right, for the natural exponential function. That's the irrational number e, okay, which plays a key role. That's an important irrational number like pi or square root of 2. It plays a key role in calculus like pi. It plays a key role in trigonometry, right? Okay, e plays an important role in calculus. Remember, the approximate value for e there is, what is that approximate value for e? If I can get this thing to write again. Yeah. It's about 2.71828, I think, are the next two digits. And then it's an irrational number, so it doesn't terminate, right? The decimal expansion doesn't terminate, and it doesn't repeat either, because it's an irrational number. You know, irrational numbers have non-terminating, non-repeating decimal expansions, okay? So numbers like square root of 2 or pi, when you write out their decimal expansion, they don't terminate and they don't repeat either. So it kind of makes them hard to work with in decimal for that reason. Now, that's the natural exponential function. Remember, that function is always increasing from left to right, so it has an inverse, and the inverse is the natural log function, which we denote this way. Okay. So you can think of ln as being a kind of a reverse acronym there for natural log function. You can also write it out this way in this format as well. This is kind of an abbreviation for that kind of longer way of writing down the natural log function. You read this as log base e, but the short name for that is natural log. So these functions are inverses of one another. When you compose them, they're going to cancel each other. And these functions are true inverses of one another, so you don't have this issue of like we have with inverse trig functions. All right, so the natural log function has many important and useful properties. Okay, so as a function, it's kind of unusual because it obeys these properties. Most functions do not obey these properties that I'm writing down, and then but the fact that it does obey these properties makes it really helps us when we're using the natural log function. It's not always easy to use the natural log function because it doesn't have a formula for it. Okay, right? It doesn't have a formula. Really, the way the natural log function is created is as the inverse of the natural exponential function. The natural exponential does have a formula. There's its formula, e to the x power, but the natural log function does not have a nice formula. But it doesn't obey these nice properties. This first property A is just simply based on the fact that the natural log function and the natural exponential function are inverses of one another. When you apply the natural log function, right, to the natural exponential function, in other words, when you compose them, they're going to cancel each other, and you just get left with input. So a natural log of e raised to a power is just going to result in that power. This is just composing in the opposite way. All right. If you raise e to the natural log of a number, they cancel each other again, and you just get the number back. So these two equations just come about because the natural exponential function and the natural log function are inverses of one another. Now, these next properties, C, D, and E, are a little bit more complicated in how they come about. We're not going to prove them, but we're certainly going to use them because they are very useful. So that this first property says if you have natural log of a product, so you're trying to compute the natural log of some quantity that's a product, you can break that up as the sum of the natural logs. So you can convert a product to a sum. That's very useful. All right. So the natural log of A times B is the natural log of A plus the natural log of B. And remember, equations are reflexive, right? So you can also go in this direction as well. If you have a sum of two natural logs, you can rewrite that as a product, okay? So if you have natural log of A plus the natural log of B in an expression for some reason, you can rewrite that as the natural log of A times B. Same thing happens for quotient. If you have natural log of a quotient, A divided by B, that's the same as the difference of natural logs. So if you have natural log of a fraction, you can break that up as the natural log of the top minus the natural log of the bottom. Most functions don't obey this property, right? It's not true in general. If you have any old function, if you're taking f, where f is any old function of a quotient of a fraction, right? Normally, that would not be f of the top minus f of the bottom. That's that would be unusual for that to be the case for any function, but that is true for natural log function. So usually this won't be true for most functions that we study. Certainly not true for trigonometric functions, but it does happen to be true for the natural log function. Now, this third property is kind of related to the C, all right? But it's a little bit more general than C. If you have natural log of a power, so a base and an exponent, natural log of a to the b power, okay, you can get rid of the power, all right? And the way you do that is just by bringing the exponent as a coefficient in front of the natural log, okay? So a natural log of a to the b power is the same as b times the natural log of a. You know, sometimes powers are complicated, right? And difficult to calculate. So this property is really useful sometimes because we can sort of undo the power and just turn it into a product of with a coefficient. So that can be really very helpful. Now, the last line here, F, okay, is this is really the same as A, okay, but I just filled in specific values for the A here, right? So if you have natural log of E, right, think of that as natural log of e to the 1 power, because E is e to the first power, right? Okay. Well, what does property A tell you when you have natural log of e to a power? It says that the e and the natural log cancel each other, right? Okay. And what do you get left with? Just whatever the exponent is. Okay. So this is something to remember. This is just something to memorize because we often end up computing this value, the natural log of e, and the natural log of e is 1. All right, so just always keep that in mind. Natural log of e is always equal to 1. Natural log of 1 is going to turn out to be 0. Let me show you why that's the case. Because you can write 1 as e to the 0th power. Remember when you take any number and raise it to the 0th power, what do you get? 1, right? Okay. The only exception is, what's the exception here? What number can you not raise to the 0th power? 0. You cannot raise 0 to the 0th power. Okay. But e is not 0. So you can raise e to the 0th power. Any other number to the 0th power is going to give you 1. So natural log of 1 is really the same as natural log of e to the 0. And these cancel each other again, right? Because they're inverses of one another. So what do you end up with there? Just 0, all right? So there's another value that you should remember, that you should just memorize. Natural log of 1 is 0. Let me show you another way to remember the fact that natural log of 1 is equal to 0. Remember, another way of writing natural log is log base e, correct? Log base e. That means that's the same as natural log. When you compute log base e of a number, let's say we don't know what this value is, but we're going to call it temporarily here, we're going to call it y, all right? What this equation means is the fact that log base e of 1 is equal to y. What this equation means is e to the y power is equal to 1. Okay? That's what that equation is telling you. E to the y power is equal to 1. Well, if you just look at this equation, what power of e is equal to 1? Oh, it's got to be what? 0, right? So another way we can see here that natural log of 1 has to be 0, okay? Because e to the 0th power is equal to, because any number to the 0th power is equal to. All right, now these properties are going to be useful to us in helping us solve equations. That's primarily how we're going to be using the natural exponential function and the natural log function. We already saw an example, some examples of that last time. Let's try some more. All right. So suppose we're left with solving this equation. This is not one you can solve by inspection. 3 to the x plus 2 power is equal to 7. If you're trying to guess what the value of x is there, you're not going to get it right. Okay, this is not one that you can solve by inspection. By the way, we could take some guesses here. What if we said, what if we thought x is equal to 0? Maybe 0 is the solution to this equation. Is that right? Well, just check it. If you think x is 0, then when you plug 0 into this equation, you get 3 to the 0 plus 2 is equal to 7. But what is 3 to the 0 plus 2? 9, because that's 3 squared. And 9 does not equal 7. So 0 is not the solution, right? I don't think 1 is going to be the solution either. That's going to even be worse, right? If you think x is equal to 1, you have 3 to the 1 plus 2 is equal to 7. But what's 3 to the 1 plus 2? That's 3 to the third power. What's 3 to the third power? 27, yeah. So you have 27 is equal to 7, which that's even worse, right? That's way far off. So 1's not the answer. 0 not. Let's try a number smaller than 0. Let's try minus 1. Is that the right answer? So we have 3 to the minus 1 plus 2 equals 7. But what's minus 1 plus 2? 1. So we have 3 to the 1 power, which is 7. Nope, not right either, right? So missed again. Yeah, we certainly can use decimals, and the solution here is going to end up being some sort of decimal value, right? It looks like it's going to be between 0 and -1, correct? Because when you tried x being 0, you got the left-hand side was 9, a little bit too big, right? But when you tried x being -1, you got the left-hand side to be 3, which is a little bit too small. So it looks like our solution is somewhere between, it's going to be a negative number somewhere between 0 and -1, but who knows, right? Okay, so you know, not going to be able to very easily guess at what the answer is here, right? Some as Amanda says, some decimal value between 0 and -1, but who knows, right? Okay, so we certainly need to be more methodical or systematic about solving this equation. Okay, now look, notice what you've got here on the left hand side is an exponential expression, right? You've got an exponential expression. So the task here, as it's going to be in almost all of these equations, if not all these equations, the task in solving this equation is to get the x out of that blasted exponent, right? Okay, want to get the x out of that exponent so we can finally write down at the end here x equal to some quantity, right? Okay, looks like some quantity between 0 and -1. Now, notice though that this base here is not base e, so slightly bigger than e. This is 3, e is 2.718, right? Okay, so this left-hand side is not a natural exponential because it does not have base e, it has base 3. But you can form exponential functions from any base. It doesn't have to be base e. Base e is just the most famous one because it's the most useful one, all right? But you can also form an exponential function with base 3. The base 3 exponential function also has an inverse. Guess what it's called? They're all called what? It's a big piece of wood. A log, they're all called log, right? Okay. But the log I'm going to start using here at first is not going to be log base e. That's natural log. I'm going to use the log base 3 function. There is a log base 3 function. And you write it down. Just like you write down log base e, except you put a 3 there instead of a, right? So I'm going to apply that to both sides of this equation. What happens on the left-hand side? By design, what's going to happen? What? Yeah, that's right. These things are going to cancel each other, right? This is the base 3 exponential function. Its inverse is the log base 3 function. These things are inverses, so they cancel each other. All right, they cancel each other. That's the purpose of having log functions, okay, is as inverses of exponential functions. They have other purposes as well, but that's one of the purposes. So guess what you get on the left-hand side here? Just x plus 2, that's right, is equal to log base 3 of 7. And now just subtract 2 from both sides, right? I'm going to think of that as adding minus 2 to both sides. So, Amanda, there is my solution. That's the number. But that's not a very satisfying solution, okay? Now, we could make it more satisfying if we could calculate log base 3 of 7, right? So if we had some device of computing log base 3 of 7. But we usually don't calculate log base 3 of numbers on your calculator. You won't have log base 3, right? What bases do you have on your calculator for computing log? Log base 10, that's the LOG key. That's the common log. And then what's the other one? You don't have 2 usually on the calculator. Log base 2, that's an important logarithm. That's called the binary logarithm. You don't even have that on the calculator. What's the only 2 things you have on the calculator? You have log base 10, that's the LOG key. What's the other log key you have on the calculator? What? ln, that's log base e, right? Okay, so you get either log base 10 or you get log base e, ln, but calculators don't compute log base 3 because whoever uses log base 3, right, is not very useful, all right? So there's no reason to put a log base 3 key on your calculator. So we're going to have to go back to the drawing board. That's my point. But this is a valid solution. This is a valid solution. Okay. Whatever that number is, I'm thinking it's somewhere between 0 and minus 1, right? That is the solution to this equation. All right. So let's go back to the drawing board here. Let me try writing here. So I mean, I got the answer there, but it wasn't very useful to me because of not being really able to easily calculate log base 3. So let's try a log that we can calculate, all right? And what can we calculate? Natural log, right? Or log base 10, but let's use natural log, all right? So well, here's what I'm going to do. I'm going to apply the natural log to both sides, just like I did above. Now, look, Amanda, these things do not cancel each other because these are not inverses, all right? So sadly, I cannot cancel these things out and just write down on the left-hand side x plus 2 because this is log base e and this is exponent base 3, right? Which is not the same as e. So we appear to have hit a block here, right? Okay, a barrier here, but we haven't because we need to remember our very useful property here. Okay, that property says if you're computing natural log, actually any log obeys this property, but in particular natural log of a power, what can you do with the exponent? Move it to the front as a coefficient. So I always call this the exponent to coefficient property. There's another name for this too. Exponent to coefficient. The exponent becomes this multiple in front, this coefficient in front. That still applies here, even though the bases are different, right? Natural log is log base e, and this is base 3. So you can take the entire exponent here, the x plus 2, and you can bring it in front. Be sure you bring the whole thing. So now we have x plus 2 times the natural log of 3 is equal to the natural log of 7. But these numbers you can calculate with your calculator. So you see we've made progress. All right, now let's finish trying to solve this equation though. Remember, we've got to solve for x. So we have to be patient here. Let's multiply let's multiply the natural log of 3 through here. So I have x times natural log of 3 plus 2 times the natural log of 3 is equal to natural log of 7. This is just a number. It doesn't involve x. So you can pull that to the right-hand side. So you have x times the natural log of 3 is equal to natural log of 7 minus 2 times the natural log of 3. And now how do you finish solving for x there? I got to get x by itself. So what do? Divide, right, okay, by natural log of 3. So divide both sides by natural log of 3. Oh, so there's another way of writing down our answer. It looks a lot different than this one, but they really are the same numbers, believe it or not. Hard to believe, but they are. So there also is my solution. Can y'all read that? Natural log of 7 minus 2 times the natural log of 3 divided by natural log of 3. Don't divide out this natural log of 3 here because that natural log of 3 would have to also divide into the natural log of 7, which it doesn't. So you have to leave it just in this form. Now, that's a little bit messy. It's a little bit messier than our original solution, right? But what's the advantage of this answer? Nothing divides out. But what, Evan? Well, this is an actual number too, okay? But this actual number has an advantage over this actual number. What's the advantage? No. No. No, the advantage here is you can calculate with your calculator natural log of 7 and natural log of 3. So you can get a decimal approximation for this solution. This one we were kind of hung up on, right? Because we couldn't use the calculator to compute log base 3 of 7 because we don't have log base 3 on our calculator. All right, so can y'all fill those in for me? Natural log of 7 minus 2 times the natural log of 3 divided by natural log of 3. I hope it comes out between approximately between 0 and -1. If it doesn't, we're in trouble here. Not? Sonny, what is it? Did you get it? Negative point what? That's small? 0.54? I didn't think it would be that small. Someone else get the same thing?
No, I got negative 0.228.
Ravi got, is that Ravi? Ravi says minus 0.228.
No, this is Fernando.
Oh, Fernando, okay. Minus 0.228, anybody else? So we've got a dispute here. Okay, good. Y'all stay minus 0.228. All right. Well, let's try checking that answer by actually substituting it back into the original equation. Okay. Now that means we have to be able to raise 3 to a power. So I hope on your calculator you know how to raise 3 to a power. Not sure I know how to do it on this calculator. Right. Usually it's an x to the y key or an exp key. Something like that. All right, but let's try plugging this in and see what happens. So what we're thinking our answer is minus 0.228. So I have 3 to the minus 0.228 plus 2, right? And let's see if that comes out to be about 7. So there's the minus 0.228 plus 2. So that's 1.772, right? So we have 3 to the 1.772. Let's see if we can raise 3 to that power. I do have a y to the x key. If I can. Yeah, I think I used it right. I got 7.0058, but remember 1.77, the minus 0.228 was an approximation, right? Okay. So I think we got it there. Yay, right? There's the exact answer. And there's decimal approximation to decimal places. Okay, so in solving this equation, right, where you have your unknown in an exponent, what's the big trick? So in solving this equation where your unknown x is in an exponent and you've got to get it out of the exponent, what's the key step there? There were several steps, but what was the key one that really unlocks this problem for us? Moving it to the front, Amanda, that's right. But what did we do first before we were able to move the x plus 2 down to the front? I couldn't just do that immediately, right? You can't just take the x plus 2 down here, right, immediately. Now, what did we have to do first? It's really important, so I've got to get you to say it. What? Here's where we were, right? What did we do first before we were able to move the x plus 2 down? What now? That's right. We took the natural log of both sides. Yeah, took the natural log of both sides. So we had to take the natural log of both sides first. Okay, that then allowed us to free the exponent, right, as a coefficient. That's going to be crucial. All right, let's look at the next one then. Okay, and so see, we're in the same boat, right? We have the same problem. We have e to the 2x power, and that unknown x that we're solving for is in the exponent. So ultimately, right, that x has to get out of the exponent so we can see what our solution to this equation is, right? So we know what the game is. We're going to do what first, ultimately, or I mean, not ultimately, but do what to get the x out? Take the natural log. Now, you could haul off and take the natural log here first, all right? But let me show you what the problem with that is. So if you start here immediately by taking the natural log of both sides, I mean, that's going to be the impulse to do that. The problem is that that 8 coefficient there, that prevents you from canceling the natural log in b. All right, so you won't be able to do anything with quite with this equation with the 8 there. All right, so my recommendation is get rid of the 8 first. It's not really my recommendation, it's really necessary here. First, to get rid of the 8 from the left-hand side. How can you get rid of the 8 from the left-hand side? Divide. Yeah, that 8 is just multiplied in, right? So you can just divide both sides by 8. So start here by dividing both sides by 8. So you won't have a coefficient on the e to the power. All right. So you get e to the 2x is equal to 20 over 8. That reduces to something. What is that? 5/2. 4 goes into both of those numbers. So we have this. Now you can apply the natural log to both sides. So you have natural log of e to the 2x equal natural log of 5/2. Now in this equation, you have a luxury. You can do 2 different things. These functions are inverses of one another. This natural log is log base e, right? And this power is base e. So these will cancel each other, and you'll just get left with 2x, right? We couldn't do that on the in this equation, right? When we applied natural log, because we had natural log of exponent base 3. But this is natural log of exponent base e. These are inverses of one another. So you can cancel and just get 2x is natural log of 5/2. By the way, natural log of 5/2, that's natural log of a quotient, right? So that is the same as natural log of 5 minus natural log of 2. Remember, when you have log of a quotient, you can break that up as difference of the two logarithms. But now, anyway, if you don't do that, it's okay, though. How do you go ahead and finish solving for x here? Divide by 2, right? Just to get rid of the 2. So you have natural log of 5 minus the natural log of 2. All of that divided by 2. So now that's easy to calculate. This one is easy to calculate with calculator, right? Okay. Just take natural log of 5 minus natural log of 2, and then divide all of that by 2. I get 0.458. Is that what, did someone else get that? 0.458. So I think our approximate answer there is 0.458. Is that it? Okay. So that's a decimal approximation, 0.458 to 3 decimal places. This is the exact answer. So this is exactly correct. So think about this when you're entering answers in WebAssign, right? If WebAssign wanted the exact answer, you would have to enter this expression. That's the exact answer. This is only the decimal approximation. Now, I said there was one of 2 ways you could proceed here from this point after you've taken the natural log of both sides. Let me show you the other thing you could have done here. You could think, oh, natural log of e to the 2x. Oh, so that's natural log of a power. So I can bring the 2x down, right? I can bring the 2x down in front. So I would have 2x times the natural log of e is equal to natural log of 5/2. But then you have to remember, how much is natural log of e? That was one of the values that I told you should remember. Natural log of e is always what? There it is. Natural log of e always what? 1. So since natural log of e is 1, guess what you just get here? Again, 2x, right? So you end up at the same place. You just might think about solving you just might think about the steps differently in the solution of the equation. All right, here's one I'm going to let y'all do. Okay, so but let's remind ourselves what we want to do first here. Okay, so I have 5 times this power, 2 to the 3 minus 2x is equal to 10. Okay, so and you want to solve for x, right? So you've got that x in the power, right? The x is in the exponent, and you got to get that out, right? Okay, so what would we do first here, though, to unleash that x, so to speak, so I can free that x from the exponent and ultimately get an expression for my answer? So what do I want to do first here? Divide by 5, right? Yeah, get the 5 out of the way first, all right? So divide both sides by 5, okay? And then that's easy to divide both sides by 5 in this case. So you can divide by 5, and then the key step is what? ln, right? Yeah, okay. Apply natural log, right? Okay, so apply natural log. Now be careful here when you apply natural log, because the natural log of 2 is not, natural log and 2 are not going to cancel each other, right? So you will have to think of this one as bringing the exponent down, all right? Okay, but Amanda's right. Natural log of both sides. That after you divide by 5, natural log of both sides. Next step. All right, so y'all try that. And you can write down what the exact answer is, right? And then see if you can get a decimal approximation with your calculator. You almost always need a decimal approximation. These questions, because strange expression answer the same. Have no idea what the numbers are. Okay, you guys at home too, right? So see if y'all can solve that equation. Give me the exact answer for x, and then just what is it in decimal terms? Still minus. Okay. So we didn't have to write one. That's easy. So go back to the yeah.
Oh, I thought. I guess it's because I.
Yeah, right. But now we minus 3. Still have this money.
Yes. -2. Oh, yeah, -1. Actually.
Minus 3. That takes the log of both sides, but not log base 2, natural.
So. Oh, I just did that.
Yeah, you can simplify.
I figured that. Okay, gotcha.
That
That's
or
the basic.
natural.
You know.
Not log base 2.
Yeah, they will.
Tell it. Or do the other one? No, that's one. He is. Yeah. Talk about that. First divide. And right back. Okay, bye. So how do you do it? Right? Yes. Now.
Find you.
Natural.
I have rebel.
All right, let's see what you guys did. All right. So we mentioned, right, that first thing we want to do there is divide both sides by 5, right? So we get 2 to the 3 minus x equals 2. And now we have to get the 3 minus x out of the exponent. So what allows us to do that, the trick that allows us to do that, right, is to take the natural log of both sides, correct? So let me squeeze that in here. Take the natural log of both sides. And now we know that property that for natural logs, right, that says, oh, you can take, if you have natural log of a power, you can bring the exponent down as a coefficient, right? So you have 3 minus x times the natural log of 2 is equal to natural log of 2. Now, what I was showing y'all when I was walking around the class is some of y'all were taking the natural log and you were multiplying it times the 3 and multiplying it times the x, which is fine. That's okay. But we have a little bit of a break here because we have natural log of 2 on both sides, right? We can just divide both sides by natural log of 2. So that won't always happen, but happens in this particular problem, right? Divide both sides by natural log of 2. And so you get 3 minus x equals to natural log of 2 over natural log of 2 is 1. So we just end up with 3 minus x equals 1. And now that equation is easy to solve, right? When you solve that, you get x equals 2. Okay. So there's so we don't need a decimal approximation there. The answer is very easy. It's just 2. Okay. You guys can check that. This one's easy to check. If you take that 2 and plug it back in for x, in the original equation, you have 5 times 2 to the 3 minus 2. Well, 2 to the 3 minus 2 is 1, right? So 2 to the 1 is 2 to the just 2 to the first power. That's 2. So what this boils down to is 5 times 2 is equal to 10, which is correct, right? Okay. So so we know we got the right answer there. Right? It's equals 2. Okay, let's try another one. And this one's a little bit more complicated, but really not. All right. We're going to. Okay, so see, this one looks terrible, but because it's just a complicated expression here on the left-hand side, right? But this is where you need to you need to remember your algebra to help you solve this equation. To solve this, try factoring the left-hand side. Okay. The reason you can do that is you have the left-hand side equal 0. If that weren't equal to 0, what I'm getting ready to show you here would not work. But because you have the equation set equal to 0, you can factor on the left-hand side. And this does factor. What can you factor from these two terms? A couple of things, actually. So out of these two terms, what can you factor out in front? So you'll have the left-hand side looking like this. Something times a quantity in parentheses equals 0. What common factors do you have in both of these terms? E to the x, right? So you know you can factor out an e to the x. That's not it, though. There's something more. What else can you factor out? What else do you have in common in both of those terms? What? X, right. You can also factor out an x. So we can factor out in front here x and e to the x. Now, what's left when we factor out x and e to the x? Well, from this term, you just have a 3. And what's left here? The e to the x is gone. One of the x's is gone. So you just have an x. So this equation factors nicely as x times e to the x times 3 plus x equals 0. Whenever you have a product equals 0, so I've said this now lots of times, but it's worth repeating because it's so important in solving equations. Whenever you have a product that equals 0, that means one of the factors is 0. So what are the factors that we multiplied together here? One of them is x. So it's possible x is equal to 0. There's a solution already. There's one solution, x equals 0. Or it's possible e to the x is equal to 0. Or 3 plus x is equal to 0. This is very easy to solve. This is x equal minus 3. So there's two solutions already. Now, what about for that third equation? E to the x equals 0. E to the x, the natural exponential function, does not have any x-intercepts. We talked about this, okay? You cannot raise any base other than 0 to a power, any base, much less e, to a power and ever get 0, okay? No number to a power is going to be 0 except unless the base is 0. So this has no solutions. There's no possible x here that will make e to the x equal 0. So there are your two solutions, x equals 0 and x equals minus 3. That's it. See, it's easy to solve. Didn't even need natural log there at all, right? That we just solved using some algebra. Okay, well, I've got one for y'all. So I think coming up. So we're going to do that when we get back. Let's take a break, though, for a few minutes here. And then we'll come back and look at, I'll give y'all one, I think. I've got one in my notes here coming up, all right? One last example here of solving these another example of solving exponential equations. But we've got still some more examples to work through, okay? All right, so let me pause the recording there, and we'll come back in. Okay, let's turn the machine back on and see if we can try this problem, right? X times e to the x minus 2x is equal to 0. Okay, so wonder what solutions we have there. All right, so this one is deceptively simple. That doesn't look like that complicated an equation to solve, but it does involve a lot of the principles that we have solving equations that we used, either that we just learned or that we've been using since the beginning, right? So see if you can think about solving that equation. It's going to involve some factoring, right? So don't forget about that, right? Okay, you're in perfect situation for factoring here, right? Because you've got the equation set to 0. That's what you need so that you can solve an equation by factoring. If you don't have the equation set to 0, that's not usually going to work, right? Okay, so start on that one. Walk around, observe your experience while you're doing that. You guys at home also, right? So x e to the x minus 2 to the x. I'm sorry, minus 2x equals 0. You guys work on that. Fine. Okay. Factor. Send factor. Yes, yeah. So there's one solution. Yeah, now it's something. Yeah, right. There you go. Right? So, there you go. Yeah. So there you go. Yes. Okay. That's all. That will happen. That was. Oh, yeah. There you go. That's right. Not just divide out. Factor out. Set your factor. So I did both sides. So yeah. So, okay, that's what we saw this. Okay, so, right. Oh, yeah. This is a errors now. You know, what is that? This one. So yeah, see what I saw. That's a natural. Oh, we actually. Oh, yeah. Okay, so I'm passing around the signature sheet. All right, y'all are doing that nicely. So let's see. Let's see what happens here when we solve this equation. So as I recommended, right? Let's try, as I recommended there, right? Let's try factoring. So we can factor x from both of these terms. So you have x times e to the x minus 2 equals 0. And now, see, there you have a product. There you have a product that equals 0. So that means one of the factors is 0. So either x is 0, there's already one solution popping up, right? X equals 0 is the solution to this equation. Or e to the x minus 2 is equal to 0. So we just are left with solving this equation. I think add 2 to both sides, right? So you have e to the x is equal to 2. And now to get the x out of the exponent, take the natural log of both sides. So you have natural log of e to the x equals natural log of 2. Now, to simplify natural log of e to the x, you can think of that in two ways. The more direct way is just remember natural log and e to the x, those functions are inverses of one another. So they will cancel each other, and you'll just get left with x equals natural log of 2. Another way to think of it, though, is using that exponent to coefficient property, right? You can bring the x down in front. So you would have x times the natural log of e equals natural log of 2. But then you have to recall, oh, natural log of e, that's 1 always. So we have x times 1 is equal to natural log of 2, or x equals natural log of 2. So there's really, there's a couple of ways of simplifying the natural log of e. But anyway, you still come up with this answer, x equal natural log of 2, and then you can use your calculator, right, to get a decimal approximation for what is the natural log of 2. That's kind of a useful number to have calculated. 0.693. Yeah, that number shows up a lot, natural log of 2. And it's approximately 0.693. Okay. Now let's look at some where we have to go the other direction. Okay. So here are some equations that don't have exponentials in them. Instead, the equations start with natural log. So suppose we want to solve natural log of x is equal to 8. So just remember, what is the inverse of natural log? E to a power, right? So what we're going to do is raise e to both sides of this equation. See, I'm going to raise e to the natural log of x, and then also e to the 8th power. So notice I'm not dividing both sides by e. I'm raising e to the power of both sides of this equation. And then what happens here magically on the left-hand side? They cancel, right? Because these are inverses of one another. These functions are inverses of one another. So you just get x, and the answer is x equal e to the 8th. And that's just a number you can calculate with your calculator. It's a pretty big number that you can calculate with your calculator. Just raise e to the 8th power. But the exact value is, I mean, you can get a decimal approximation, but the exact number, exact solution is e to the 8th power, whatever that is. All right, so y'all tried this one. You're going to use exactly the same idea, right? Okay. You have natural log of 25 minus x is equal to 3. So you see the difficulty is here to solve for x, right? I've got to get the x out of the natural log. So somehow I've got to get rid of the natural log, in other words, right? To free the x, right? So I can solve for x. The question is, how do you undo natural log? Well, we know how to undo that, right? Okay. Because we know what its inverse is, right? Imagine. I think y'all did that really easily. Did y'all get that at home? Did y'all come up with an answer? Can y'all tell me what the answer is? Someone on Zoom? Just the exact answer, and then we can compute what that is approximately. Someone have that there? I know you guys are smart out there, so. Someone tell me about what that is. What X is. Ah, right, Kenneth. So minus E cubed plus 25, or so minus E cubed plus 25, right? Which you could write as 25 minus E cubed also, right? Okay. So you just take the number E on your calculator, cube it, and then subtract that from 25. What does that turn out to be approximately? What have 4 point what? 4.91. Oh, good. All right. So there's our approximate solution, 4.91. So how did we arrive at that? We have to, again, undo that natural log, right? So the way you do that is raising E to both sides. And then, because these are inverses of one another, just get on the left-hand side, 25 minus X. And then on the right-hand side, of course, you have E cubed. And then you just solve this equation for X. And so that's what Kenneth solved that equation for X. So we got minus E cubed there, plus 25. All right, now in this next example, we're going to ultimately do the same thing, but we have to rearrange the equation a little bit first before this trick of raising E to both sides is going to work. But we still have the same problem as in this equation, right? You have natural log of a quantity, and that quantity unfortunately involves X, your unknown. So you have to get the X out of the natural log, and that's going to mean at some point you're going to have to use E to a natural log, right? Okay, but before we can do that, we need to rearrange the equation somewhat to get it in a convenient form. What you want before you raise E to both sides of the equation is you just want natural log of something equal something. You don't want this 3 multiplied times the natural log, and you don't want the 4 there, okay? So move terms around or add, or multiply or divide by whatever it takes so that you can get the equation looking like this before you then raise E to both sides, right? Okay, so let's see, what can we do? I think that seems pretty easy here, right? I need to get the 4 off of the left-hand side. So let's move the 4 over to the right. So we get 3 times natural log of 2x is equal to 16 minus 4, which of course is 12. And then I need to get rid of the 3, right? So that's easily done also. You can't subtract the 3 because it's multiplied in. So you just divide out the 3. So you end up with natural log of 2 times x equals, what is this? 12 divided by 3, which is 4. Now we have it in the shape that we were hoping for, right? We just have natural log right by itself on one side of the equation. And so now we can raise E to both sides so that we can undo that natural log. So again, you get this big power of E. Well, it's not that big. E to the 4th power on the right-hand side. And on the left-hand side, it's easy though, right? We just get 2x. So 2x equal E to the 4th power. And now just divide both sides by 2, right? To finish solving for x. So you have E to the 4th power divided by 2. Let's see, how much is E to the 4th power divided by 2? E to the 4th power is going to be 60 or 70, something like that. I don't know. You'll try it with the calculator there. Yeah. 27 point, yeah, 3 about. It's actually 299 if we write down all 3 decimal places, but that's very close to 3, right? So if I can squeeze, I can't squeeze that in. So 27.299 is our approximate answer. It's pretty, see, that's again straightforward. You just have to remember though to clean up the equation a little bit first, right? Before you raise e to both sides. That's the most common mistake now that students will make in trying to solve an equation like this that involves a logarithm. Is forgetting, oh, I've got to get the equation in the right form before I can raise e to both sides. All right, let's try this one. So again, see, what I want is I want to be able to raise e to both sides of the equation. But before I do that, I need to have a single natural log on one side of the equation. I can't have 2 natural logs here. All right. So is there some way we can combine these 2 natural logs into a single natural log? What, Iris? Not factor. I won't be able to factor here, but remember, one of our properties for logarithms said if you have log of a product, right? Let's go back to that one. If you have log of a product, that's the same as, see, scroll all the way back up here. We have log of a, there it is. If we have log of a product, that's the same as the sum of the logs. Now, we didn't have log of a product, but we had sum of logs in that equation. So we're going to apply this property backwards, right? I'm pointing here, right? Yeah, you multiply them. That's right. Okay. And that will give you a single logarithm, though. That's what we want. Okay. On the left-hand side, a single log before I raise e to both sides. So if I can get back down there, if I can find my scroll bar here. There it is, right? So you see there you had sum of logarithms, right? So you can rewrite that as log of a product. So it's natural log of x plus 2 times x minus 1 equal 0. Okay. Now we're in great shape. Single natural log here equals 0. So how can I get rid of the natural log? E, right. So I get e to the natural log of x plus 2 times x minus 1 equal. Now here you have to be careful. Raise e also to the 0th power. So what does that give you on the left-hand side? Yeah, you have x plus 2 times x minus 1 equals, but what's e to the 0th power? 1. So you end up with this. So we still have some work to do because we still have this equation to solve, okay? But it doesn't have natural logs. So we've made some progress here, all right? This is just a plain old algebraic equation, doesn't have any natural logs in it. So we hopefully will be able to solve that using just our algebraic knowledge, right? Okay, I think we can. But look, do not make the following mistake, okay? Because here's the mistake you're going to want to make. And I don't want you to do this. You're thinking, oh, I have this product that equals 1, right? I have x plus 2 times x minus 1 equal 1. So you're going to think, oh, that means x plus 2 is equal to 1, or x minus 1 is equal to 1. That's very convenient. And then I just solve those 2 equations. Yeah, but Emil, you're shaking your head. Why can I not do that? Yes, well, that's correct, right? It's not how it works. How does it work, right? For me to go from here to here, what would this equation have to look like? It can't, it's got to be 0, right? Yeah, okay. It doesn't work if I have x plus 2 times x minus 1 equal to any other number other than 0. I can't make this step, okay? See, the reason is if you, here's a good lesson, and I've said this many times. If you have two quantities together, no matter what, multiplied together, no matter what they are, if you have a times b equals 0, you do know that a is 0 or b is 0, right? That's the only way you get a product equals 0 is if one of the factors equals 0. Unfortunately, that's not what we have here. We have a times b is equal to 1. Can you think of two numbers multiplied together to give you 1, neither one of which is 1? See, here I'm saying if two numbers together multiplied together give me 0, one of them's got to be 0. But it's not the case that if two numbers multiplied together give you 1, one of the numbers has to be 1. Can you think of an example where that wouldn't be the case? I multiply two numbers together, I get 1, but neither of the numbers is 1. Like what? .5. Yeah, a could be 0.5 and not 4, but what? 2. There you go, right? If a is 0.5 and b is 2, their product is going to be 1. But see, neither one of these numbers is 1. So it's not valid to say, oh, darn it, one of these things has to be 1. So can't make this jump. What am I going to have to do, though? So that doesn't work, but that doesn't mean I'm at the end of my rope. What will I have to do here to solve this equation? I just have to be a little bit more patient. So what can I do here? Distribute, right? Yeah, go ahead and distribute the x plus 2 times the x minus 1. Multiply those things together. That's going to give you x squared plus x minus 2 when you're finished. Okay, equals 1. All right. And now subtract 1 from both sides. So you get x squared plus x minus 3 equals 0. Now you're in a position where you might be able to solve the equation. Well, how can we solve an equation like that? X squared plus x minus 3 equals 0. One way is to do what? Take this factor. So factor it again, right? So refactor here, x squared plus x minus 3. Unfortunately, that will not factor, okay? So x squared plus x minus 3 does not factor. So again, you may think, oh, I'm at the end of my rope. I can't solve this. No, 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 no. You do know how to solve it. What is your alternative here? If you cannot solve this by factoring, quadratic formula. That's right. You can always use quadratic formula. You have to remember the quadratic formula, but you use the quadratic formula. Y'all remember the quadratic formula? Well, if you yeah, if you don't, you're going to have to remember it because we're getting ready to talk about the quadratic formula in much greater detail than we have so far in the class as soon as we finish these notes. But here's the quadratic formula. It says if you're solving a quadratic equation, that's an equation with x squared in it, that it's set equal to 0, got to be set equal to 0, then here are what the solutions look like. You get two solutions. They're kind of messy, but there are two of them. Yeah. And the A, B, and C are just the coefficients in the equation. This is the this coefficient is the A, this coefficient is the B, this last constant is the C. Let's plug those in then and see what we get. So we get what? What's our B value here for this equation? Yeah, not x, it's 1, right? So you get minus 1 plus or minus the square root of 1 squared minus 4 times what's the A? That's this coefficient, 1. And what's the C? Minus 3. Remember to keep the sign there. Over 2 times 1. Well, let's see what this is. minus 1 plus or minus the square root of 1 and minus 4 times 1 is minus 4 times minus 3 is plus 12, right? So you have 1 plus 12 over 2. Well, there it is. Minus 1 plus or minus the square root of 13 over 2. Wow. Who would have thought you were going to end up with those numbers as solutions to this equation? Okay, so one solution is minus 1 plus the square root of 13 over 2. The other one is minus 1 minus the square root of 13 over 2. And of course, you can get a decimal approximation for square root of 13 using your calculator, since 13 is not a perfect square, right? And then you can get a decimal approximation for two solutions. This is in exact form, though, so let's leave exact form. So we have two answers there. Wow, that's really a workout there. We learned we had to use inverse of natural log, which is the exponential function, right? And we also had to use the quadratic formula. A lot of things combined in that problem. I don't think this one is quite so bad. So I'm going to let y'all do this one. Looks terrible, but it's not really all that bad. See if y'all can solve this equation. So let me give you just a hint of how things are going to go. You'll have to eventually get rid of the natural logs, right? That means you've got to raise e to both sides of the equation at some point. But before you do that, you want the equation to have just a single natural log on both sides. If you get just a single natural log on both sides, then you can raise e to both sides and then proceed from there. So you have to get a single natural log, right? I think you know how to do that now from the previous example, right? Where you raise e to both sides. And then you're left with an equation to solve, but I don't think it's going to be all that bad. It's not going to use the quadratic formula. Looks like it will, but it won't. All right, so probably working with that one. Okay. Okay. Yeah. Okay. Where you want to be, right? And how do you get rid of? Yeah.
We want to
Yeah. So something can happen. Right. So. Okay. So it's natural law. And so what's that? Yeah. Yeah, now just I'm trying. So I'm set it to 0. Yeah. Yeah, you can solve this right? Doesn't you said put on this side. So then you'll have an equation. How you guess what? Okay. And goes up. Okay. All right, so while you guys are finishing up the last couple of expressions there, I think everyone's on the right track. So what we did here, right, was we combined these two logarithms, right, into a product because we had sum of logarithms. Remember, sum of logarithms is the logarithm of the product. So the right-hand side you can write is just the natural log of x plus 2 times x plus 3. And now since you have this single natural log on both sides of the equation, now you're free to raise e to both sides of the equation so that those things will undo each other, right? They'll invert each other. So you end up with, you can drop the parentheses at this point, just x squared plus 1 on the left-hand side equals this product x plus 2 times x plus 3. And that still looks like that might be a hard equation to solve, but at least it doesn't have natural logs in it, right? Okay, so made this progress. You just have this algebraic equation to solve now, okay? And that you're much better equipped to solve. So let's see, x squared plus 1 equal, let's multiply out these parentheses. When you do that, you'll get ultimately x squared plus 5x plus 6. I skipped kind of a step there, but that's ultimately what the right-hand side will simplify to. And now, if you want to, you can try setting this to 0. You're thinking, I'll have to set this to 0 because I have some x squareds here, right? So let's move everything to the left-hand side. So I get minus x squared minus 5x minus 6 equals 0. But now we see, oh, I really don't have a quadratic equation because these x squareds cancel each other. So it's really an easy equation. I have minus 5x minus 6 plus 1 is minus 5 equals 0. And now see, this is a really easy equation to solve, right? You can shift the minus 5 to the right-hand side, so you get a minus 5x is equal to positive 5, and then just divide both sides by minus 5. So you end up with x equal minus 1. Is that what y'all got? X equal minus 1? Okay. I do need to caution you, sometimes it doesn't show up in this problem, but it may come up in the homework. When you're solving these equations that involve natural log, you should go back and plug your answer in to make sure that when you plug your answer in, you don't end up trying to take natural log of a negative quantity. You cannot take natural log of a negative quantity. The domain of the natural log function starts at 0. We showed that last time, but you probably forgot. The domain of the natural log function only 0 to infinity, not including 0. Can't even compute natural log of 0. So if you ever try to compute natural log of a negative number, if you try that with your calculator, it'll say error, right? Keep that in mind also, just when you're doing it on the page. Cannot compute natural log of 0 or natural log of a negative quantity either, okay? So if we had plugged the minus 1 in here, if we were checking the solution, if we had plugged the minus 1 in and we ended up with natural log of a negative number, we would have to toss out that solution. That sometimes happens in solving natural log equations. That's called an extraneous solution. This is not an extraneous solution, however. This one is okay. But you may end up with extraneous solution in your homework. All right, I think we're out of notes there. Oh, yeah, we are. Okay. We have just a few minutes, so I'm going to switch to the next notes just to start this, but we won't get very far into this. We're not, so we're done with exponential and logarithmic functions. We don't spend much time with that. We also going to talk about another type of function here called polynomial functions. So these are not trigonometric functions, polynomial functions. And you're actually familiar with polynomial functions, not just from previous courses. You're probably familiar with from previous courses, but also from this course, because we've already been using polynomial functions in the class. We just didn't call them what? We didn't call them polynomial functions, okay? But we've already been working with polynomial functions because linear functions are examples of polynomial functions. So linear functions count as polynomial functions. What do linear functions look like, remember? Well, if you just have a number, a y equal to a constant, that's a linear function. Remember, y equal constant, the graph is a horizontal line. So if you have y equal to a constant, that's a linear function. Or also, the more familiar linear functions look like this, right? Where we have mx plus b, right? Now, if you add on an extra power of x here, you get functions that look like this. So if you take a linear function where you just have x to the first power, right? And if you add on also x to the second power, a term involving x to the second power, that is called a quadratic function because you have the x squared in it, right? When you graph a quadratic function, you get not a straight line, but you get a parabola, a curve that looks like this. It's a U-shaped curve. It either opens downward or it opens up, but it's a very simple curve like this. It has one turning point on it, either at the top or at the bottom, one turning point. Quadratic functions, which I know you've looked at in other classes, they also count as polynomial functions. So notice all we did here when we were moving from this simple constant function up to this quadratic function, notice in the formulas, I just added in an extra power of x. If you keep adding in higher and higher powers of x, you get, of course, different formulas, but you get also what is called a polynomial function. So any function whose formula is formed just from powers of x, that is called a polynomial function. So linear functions, which just involve x to the first power, that's a polynomial function. Quadratic function, which involves x to the second power, that is also a polynomial function. But if you add in higher and higher powers of x, you still get a polynomial function. So polynomial functions are kind of generalizations of linear functions or quadratic functions. Now, so here's what the formula for a polynomial function looks like. This is in very abstract form. All right. Okay. Of course, when we actually deal with polynomial functions, we'll be looking at specific examples, but here's just the abstract form of a polynomial function. You just have a power of x, okay, with some coefficient in front of it, plus another power of x with some coefficient in front of it, and so on and so forth, down to a constant at the end of the formula. I wrote that as with x to the 0th power, but what is x to the 0th power again? Remember, what's that? 1, right? Okay, so at the end here, you just have a constant, just like you have in quadratic functions and linear functions at the end. So again, if you see any functions formula that's just a sum of powers of x, that counts as a polynomial function. That's called a polynomial function. Now, because these formulas are so straightforward or so easy to form, polynomial functions are really important in mathematics. We use them a lot, okay? And they have some common properties that we're going to learn about here, okay? So the graphs of polynomial functions can be quite different, but they still have some properties in common that we're going to learn about here. Let me show you an example then of a specific polynomial function. Here's one. Okay. All right. So you see how that formula is formed? Okay. It's just a bunch of terms added, or you can think of it as subtracted, right? Okay. And all those terms are nothing more than powers of x. So you have 3x to the 3rd power, and then you have 1x to the 4th power, right? 2x squared. And then notice at the end you have 0.2, which is just a constant. Of course, if you want to think of that as a power of x, you can write that as x to the 0th power, because x to the 0th power is just 1. So also just a power of x. These powers of x can get really high in polynomial functions, okay? So they can be rather large. Hang on a minute, guys, until I get more things to say here. The highest power of x in the formula is called the degree of the polynomial, right? So whatever the highest power of x is, that's the. What's the degree of this polynomial then? Highest power. 4, yeah. I wrote the term second just to throw you off there. Okay? So the degree here is 4. The coefficient of that highest power of x, that's called the leading coefficient. So what's the leading coefficient here? 1, right. And whatever constant is added on at the end of the formula, that's called the constant coefficient. So in this case, that's 0.2, right? So what is the degree of a linear polynomial, a linear function? What's its degree? Remember, what do linear functions look like? What does their formulas look like? Yeah. So in a linear function, what's the highest power of x? 1. Yeah. So linear functions are polynomials with degree 1. Okay. The slope is the leading coefficient. All right. Slope is the. Now, that degree is going to give us lots of information about the graph of the polynomial function. So we're going to talk about that next time. But in general, graphs of polynomial functions can be quite complex. Not linear functions, okay? But higher degree polynomial functions, their graphs can be really complicated. Okay. All right. So that's what we're going to take up next time, is more of learning about polynomial functions, okay, and their features, right? Okay. Now, one nice thing that you'll be one thing that'll make you happy about polynomial functions is usually they don't have inverses. Okay? So we'll be dealing with inverses of polynomial functions. All right, guys. So I will see y'all on Monday. So finish all your homeworks, right? Bye.